Hi. In this video, we are going to look at the method of mathematical induction, but this is part 2 of the video where we'll look at some special methods of induction that you don't normally see. So there are three basic methods that I want to talk about. First is reverse induction or backward induction. So what is this? Basically, this says that let P of n be a proposition related to natural numbers n, and we suppose that first of all P of n is true for infinitely many natural numbers n. numbers n. And the second assumption is if P of k plus 1 is true, then that implies that P of k is true. Okay. So then we can say that P of n is true. P of n is true for all natural numbers. Now, notice here that the first step, the base case, is not P of 1 is true, but that P of n is true for infinitely many natural numbers. You have to show that basically for n greater than some particular value, P of n is always true. So that is satisfied for infinite n. And then you go in a backward direction. From pk plus 1's truth, you have to imply that pk is true. And then we can basically claim that the induction is complete for all natural numbers. So that is why it is called reverse induction or backward induction, because you are going from pk plus 1 to pk, right? Okay. The next type of induction that we'll see is B, which is spiral induction. So here in spiral induction, we talk about there are two propositions, that Pn and Qn be two propositions related to natural numbers. Now we suppose that first of all, P of 0 is true. And secondly, for every natural number k, if pk is true, it implies that q of k is true. And third, if q of k is true, that implies that P of k plus 1 is true. If these three conditions are satisfied, then P of n and Q of n are true for all n. So notice why it is called spiral induction. We start with the base case for P of 0. Then from P of 0's truth, we can imply Q of k's truth. P of k being true implies Q of k being true. And from Q of k being true, we can go to P of k plus 1. So that basically completes the induction of P of k, P of n. And every time P of n is true, Q of n is true. So therefore Q of n is also true for all n, right? So this is called spiral induction for two propositions, P of n and Q of n. You have similar statements of spiral induction for more than two propositions also, right? And usually you have to remember in problems, they will give you P of n and you have to construct your own Q of n. And then the spiral induction method will start working. This Q of n is basically called the companion proposition. The next and the last type of induction that I will show you is double induction. In this method, we say let P of n and m be a proposition related to mutually independent natural numbers n and m. Mutually independent natural numbers n and m. Okay. Now we suppose that first of all, p of 0 comma m is true for all natural numbers m, and similarly p of n comma 0 is true for all natural numbers n. So this is basically the base case for double induction. You have two different variables n and m, and you'll say that one of them is fixed at 0 and the other can vary over all natural numbers, and then this base case is true. And secondly, if p of n plus 1 comma m and p of m plus 1 comma n are both true, and that implies that p of n plus 1 comma m plus 1 is true. So this is the induction step here. Then p of nm is true for all values of m and n. So the base case here is you assume the truth of p of n plus 1 comma m and p of m plus 1 comma n. And from there you have to prove that this is true, p of n plus 1, m plus 1. Right? So this is your double induction method. Now we look at some examples and some questions through which we will basically apply these methods, right? So the first question is this: a sequence A1, A2 satisfies A1 equal to 0 and AN is equal to max of 1 less than equal to I less than equal to n minus 1, I plus AI plus AN minus I for n is greater than equal to 2. Find A of 200. Basically, we have to figure out what this condition means and figure out A of 200. So for that, we need the expression for A of n, right? So let's think about it. For n is equal to 2, A of 2 will be what? Max of 1 is less than equal to I is less than equal to 2 minus 1, 1. And this is I plus AI plus A2 minus I. But I can only take the value 1. So it will be I, or I is 1, 1 plus A1 plus A1, right? So notice that A1 is given. So this will be equal to 1 plus 0, which is 1. So we are getting A2 is equal to 1. And we already know A1 is equal to 0, right? Okay. Now let's find out A3. In similar manner, A3 is max of 1 is less than I is less than equal to 3 minus 1, 2. And you have I plus AI plus A3 minus I, right? And now I can take which values? I can be 1 and I can be 2. So let's calculate it separately. So when I is 1, it is 1 plus A1 plus A2, comma when I is 2, it is 2 plus A2 plus A1, right? Now notice that A1 plus A2 is equal to 1. So this is 2 and this is 3. So the maximum value of this is maximum of 2 and 3, which is equal to 3. So basically you can figure out the first few AIs, right? A1 is 0, A2 is 1, A3 is 3, A4 comes out as 6, A5 comes out as 10. And using these values, you can sort of guess what the expression for AI should be. Now, you can try it yourself, and if you guess it correctly, the AN expression should be n into n minus 1 by 2. This is my guess because it satisfies all of these values, right? It is like 4C2 is 6, 3C2 is 3, 2C1 is 2, 2C2 is 1, 3C2 is 3, 4C2 is 6, 5C2 is 10, and so on, right? 1C2 is 0. So from there, I'm guessing this an is equal to this. And now we are going to use induction to prove this. Once we prove this, we can find the value of A200, right? Okay. So let's use the second form of induction. We are saying an is equal to n into n minus 1 by 2. We have to prove this statement. And the base case n is equal to 1 implies a of 1 is equal to 0. That is already true. We know that. Now suppose a of n is equal to n into n minus 1 by 2 for all n less than equal to k. So we are using strong form of induction, right? So then when n is equal to k plus 1, in that case, a of k plus 1 will be equal to max of 1 is less than equal to I less than equal to k. It is I plus ai plus a of n minus I. So that is k plus 1 minus I. K plus 1 minus I. This is the situation here. Now, we know that ai can be written as I into I minus 1 by 2 because we have assumed that in the induction hypothesis. We know that this is true for all n less than equal to k, and here I is less than k. So we can write it as I plus I minus 1 into I by 2 plus this also actually is less than equal to k, right? Because I is greater than 1, so 1 minus I is negative. So this whole thing is less than equal to k. So we can write this as k plus 1 minus I multiplied by k minus I by 2, right? Okay, so simplifying this expression, we have max I is less 1 is less than I is less than k. And if I simplify this whole expression inside, you get this I square minus ki plus k square plus k by 2, right? Okay. Now k square plus k by 2 doesn't have an I at all. No I component is here. So what we'll say is we'll take it out of this maximization, right? So this will be equal to k square plus k by 2 plus maximum of 1 is less than I is less than equal to k, and it is I square minus ki, which is I into I minus k, right? Now think about this. I into I minus k will be negative if I is less than k and greater than 1, because I minus k will be negative, right? And it will be 0 if I is equal to k, right? So for all other values of I other than k, this quantity is negative, and for I is equal to k, it is 0. So the maximum value is obviously 0. So this term goes away, and the answer is simply k square plus k plus 2, and that is coming as a of k plus 1, right? A of k plus 1 is coming as k square, k into k plus 1 by 2, which satisfies our hypothesis that a of n should be n into n minus 1 by 2, right? Because if you put k plus 1 here, you'll get the same thing. So our induction is basically complete, and we have figured out the expression for a of n. And now you can easily find a of 200. A of 200 turns out to be, you put n is equal to 200, you get 19,900. That becomes our answer, right? Okay, let's move on to the next one. The next problem is this one. Suppose that p and p plus 2 are both prime numbers with p greater than 3. A sequence an is defined as a1 is equal to 2 and an is equal to an minus 1 plus least integer function of pan minus 1 by n. Here, this function means least integer greater than or equal to x. Greater than or equal to x. Okay. we have to prove that for n is equal to 3, 4 till p minus 1, it's it's always true that p divides, no, n divides p of an minus 1 plus 1. We have to show that n always divides this expression for n is equal to 3 to p minus 1. P and p plus 2 are prime numbers, right? Okay. So we already know a1 is 2. So let's calculate a2. a2 will be a1 plus p of a1 by 2 like this. And a1 is 2. So this is basically 2 plus p, right? But p itself is a prime number. So this will be equal to 2 plus p, right? a2 is 2 plus p we get, right? Since p is an integer. So for n is equal to 3, what do we get? A3 is equal to A2 plus P into A2 by 3, right? Now, what we can say here is this is A2 is 2 plus P plus this is P into 2 plus P by 3, right? So correct. Actually, for n is equal to 3, what do we have to show? Our induction statement is what? 3 divides P into A2 plus 1, right? This is what we need to prove. Correct. Now, PA2 plus 1 is what? PA2 plus 1 is equal to P into A2 is 2 plus P. So P plus 2 plus 1. So that is P square plus 2P plus 1. So this is equal to P plus 1 whole square, right? So we have to show that 3 divides P plus 1 whole square. Our base case. This is our base case, right? Because our induction starts from n is equal to 3. We have to show that 3 divides p plus 1 whole square. Now that is obvious because p, p plus 1 and p plus 2 are 3 consecutive integers. 3 consecutive integers, and we know that p and p plus 2 are prime numbers. So 3 cannot divide this and cannot divide this. So 3 must divide this, the middle integer, right, which is p plus 1. So if 3 divides p plus 1, it is guaranteed that 3 will divide p plus 1 whole square, right? We actually don't need to calculate this A3 at all. We just need to prove our induction step or base case of the induction, right? And we are getting it because we know A2 is p plus 2. And from there, we get p A2 plus 1 is equal to p plus 1 whole square. And because p, p plus 1 and p plus 2 are 3 consecutive integers, then 3 divides p plus 1 and therefore 3 divides p plus 1 whole square, right? Okay. So now our base case of the induction is done. So now we'll go on to the higher cases. So for 3 is less than equal to n, less than equal to p minus 1, suppose that k divides p a k minus 1 plus 1 for 3 is less than equal to k less than equal to n minus 1, right? We are taking the fact that or we are using the strong form of induction. So this statement is true for all k less than equal to n minus 1. We want to show it for the nth step, right? So if this is true, then greatest least integer less than greater than equal to a p a k minus 1 by k should be equal to p a k minus 1 plus 1 by k, right? Because we know that this is an integer. From here, it follows that k divides this. So this is an integer, and this is the next integer higher than this. think about it, you should be able to figure it out. So for all k in this range, for all k in this range, this is the value of this function, right? Therefore, p a k minus 1 plus 1 basically becomes equal to p, instead of a k minus 1, now I will write it using the original definition, so which is a k minus 2 plus p a k minus 2 by k minus 1, the least integer function, plus 1. So I'm using the definition of a k minus 1 here, right? And this again, I can rewrite as p a k minus 2 plus, I know what the value of this is, because for all integers in this range, this is true. So I can rewrite it as p a k minus 2 plus 1 by k minus 1, whole thing plus 1, right? I will simplify on the next screen. We are getting p a k minus 1 plus 1 is equal to, if you simplify this, p a k minus 2 plus p a k minus 2 plus 1 by k minus 1 plus 1. This becomes equal to p a k minus 2 plus 1 multiplied by p plus k minus 1 by k minus 1. So this is coming for all 3 is less than n is less than equal to p minus 1, right? Now, in this expression, we replace k with n. So we are getting p a n minus 1 plus 1 is equal to p plus n minus 1 into p a n minus 2 plus 1 by n minus 1. And now we focus our attention on this term. We get p plus n minus 1 by n minus 1, and we write this term by using the original definition of a n minus 2. We can show that this will be equal to p plus n minus 2 by n minus 2, so on, so on. You keep converting this using the first definition. First definition was a n was equal to, you repeat the same steps. A n was equal to a n minus 1 plus least integer function of this by n. You put back a n, n minus 2 for n here, and then simplify again. And we know this GIF least integer function value is simply p a n minus 1 plus 1 by n. So you use that and you keep repeating, you will end up getting something like this: p plus 3 by 3 p a 2 plus 1, right? So what we can show here is that this expression becomes the product of these fractions, p plus n minus 2 by n minus 2, and so on till p plus 3 by 3, and this is basically p plus 1 whole square. So p a n minus 1 plus 1 is becoming equal to this after repeated applications of the same step. Now this expression on the right hand side, you can prove is actually equal to, I'll show you on the next screen. We have p a n minus 1 plus 1 is equal to 2n to p plus 1 by p plus n, p plus 2, and p plus n p n. You can prove that this expression is equal to the RHS that I wrote on the next screen. And here we know that this is an integer. It is p plus n choose n. That is an integer. So therefore, we have n divides p a n minus 1 plus 1 multiplied by p plus n and p plus 2. Because you can multiply this on this side and you're getting this equation is equal to this product, right? So n will divide all of this because these are integers. Now, since n is less than p and p is prime, we have GCD of n and n plus p by the division algorithm is equal to GCD of n and p, and GCD of n and p is 1, right? Also, p plus 2 is a prime greater than n. So, GCD of n and p plus 2 is also 1. So if GCD of n and p plus 2 is 1 and GCD of n and n plus p is 1, then basically, therefore, n and p plus n and p plus 2 are relatively prime. And if n is relatively prime to these two terms, then therefore n must divide p of a n minus 1 plus 1. So we have proved our induction. Induction step is done here. So the point here is always like we have repeatedly applied the definition of the term and we have understood what is the least integer function of p a k minus 1 by k in the condition when we have assumed the induction hypothesis. So repeatedly applying the definition of an, we are getting it in this form. We can show that p of an minus 1 plus 1 is equal to this. And after that, it is simple because p is a prime. We can show that it is relatively prime to p plus n and p plus 2 n. Okay, so that is the next second question. Let's look at the third one. This one we'll use, basically we'll use something like a spiral induction here. So let's see. Let a sequence f of n be defined by f of n plus 2 is equal to f of n plus 1 plus f of n, and we have f of 1 is 1 and f of 2 is also 1. We have to prove that f of n plus 1 square plus f of n square is equal to f of 2n plus 1. So this is a Fibonacci sequence. Proving it is very easy for n is equal to 1. Proving this statement is obvious for n is equal to 1. I will not discuss that. So we'll now assume that proposition is true for n is equal to k. And here k is greater than equal to 2, right? So then it is sufficient to show that n is equal to k plus 1 step, right? So that if you replace it with n with k plus 1, you should get f squared k plus 2 plus f squared k plus 1 is equal to f of 2k plus 3. Then you put n is equal to k plus 1. If we show this step, because we have assumed it is true for n is equal to k, our induction will be complete. But let's simplify what we need to show here. So what is f squared k plus 2? That is the same as f of k plus 1 plus f of k whole square plus f squared k plus 1 is equal to f of 2k plus 3. And that can be simplified like this. F of k plus 1 square plus f of k square, group them together, plus 2 f of k plus 1 into f of k plus f squared k plus 1, group them together, is equal to f of 2k plus 3. We need to prove this, right? I have done nothing. I have just simplified what we need to prove using the idea that f of k plus 2 is equal to f of k plus 1 plus f of k. I've just used that here. So this is what we need to prove. Now, in order to prove this, it is sufficient. We know that f of k plus 1 whole square plus f of k square will be equal to f of 2k plus 1, right? Because we have assumed the truth of that statement for n is equal to k. So this statement is true for n is equal to k. So f of k plus 1 whole square plus f of k square is equal to f of 2k plus 1. F of 2k plus 1 plus something should be equal to f of 2k plus 3. That is what we need to show here. So it is sufficient to show that this something, this bracket 2 times f of k plus 1 into f of k plus f of k plus 1 square must be equal to f of 2k plus 2, right? Because this is the Fibonacci pattern. 2k plus 1 plus 2k plus 2 should be f of 2k plus 3. So if we can show that this part is equal to f of 2k plus 1, we are done. The proof is over, right? So I will just write it here. So it is sufficient to prove that 2 times f of k plus 1 plus f of k plus 1 square is equal to f of 2k plus 2, right? Now let's simplify this a little bit. 2 times f of k plus 1 can be written as f of k plus f of k minus 1 plus f of k plus 1 square can be written as, uh, let's just write it as it is equal to f of 2k plus 2, and then we're getting 2 f of k into f of k plus 1, f of k into f of k minus 1, plus I'm getting 1 f of k square I'll keep here, and 1 f of k square I'll combine with this. I'm just rearranging the terms of this side, left hand side, is equal to f of 2k plus 2, right? Now notice that this is equal to f of 2k plus 1, because we have assumed the hypothesis, induction hypothesis, it's true for n is equal to k, right? So this is f of 2k plus 1. So it is enough to show that this should be f of 2k, right? If we show that this is equal to f of 2k, it will fit nicely and we'll prove our statement. So this implies that we just need to show that 2f of k minus 1 plus f of k square is equal to f of 2k, right? Notice that the structure of this statement is exactly the same as the structure of this statement. The only thing I've done is replace k with k minus 1, right? So both the statements have the same structure. So now we can start doing a spiral hypothesis, a spiral induction. So the original proposition is denoted by Pn. And what is Pn? Pn was prove that f of n plus 1 square plus f of n square is equal to f of 2n plus 1. And our new proposition, our companion proposition, is our Qn. And what is Qn? Qn is 2 times f of n plus 1 into f of n plus f of n plus 1 square is equal to f of 2n plus 2. Right? This is our companion proposition. If we can show this is implied. So when n is equal to 1, it is easy to show that p of 1 and q of 1 are true. You can confirm that yourself. That is obvious. Now we'll suppose p of k and q of k are true. So what does that mean? That means f of k plus 1 square plus f of k square is equal to f of 2k plus 1. And we also know that 2 of f of k plus 1 into f of k plus f of k plus 1 whole square is equal to f of 2k plus 2, right? Then let's find out what is f of k plus 2 whole square plus f of k plus 1 whole square. So what we are trying to do is we are trying to show p of k plus 1 now, right? So this is equal to f of k plus 1 whole square plus f of k whole square plus f of k plus 1 whole square, which will be equal to f of k plus 1 whole square plus 2 f of k plus 1 into f of k plus f of k square plus f of k plus 1 whole square. Now using the fact that q of k is true, this term is equal to f of 2k plus 2, right? And using the fact that p of k is true, this term is equal to f of 2k plus 1, right? And f of 2k plus 1 plus f of 2k plus 2 is equal to f of 2k plus 3, right? these two add up to f of 2k plus 3, and that basically means that p of k plus 1 is true. So suppose p of k and q of k are true, we have proved that p of k plus 1 is true, right? Once we have p of k plus 1 is true, from there we can easily show that q of k plus 1 is also true, right? So let's write that down. Since, I'll write it on the next screen, since p of k plus 1 and q of k are true, we get these statements. We get 2 times f of k plus 2 into f of k plus 1 plus f of k plus 2 whole square. I'm trying to evaluate q of k plus 1 here, right? Is equal to 2 times f of k plus 1 plus f of k into f of k plus 1 plus f square k plus 2. Now this can be rewritten as f square k plus 1 plus f square k plus 2 plus f square k plus 1 plus 2 f of k plus 1 into f of k. Now this is equal to f of 2k plus 3, because we have just now showed that p of k plus 1 is true, plus this is equal to f of 2k plus 2, because that is my q of k, I think. Yeah, that is q of k. So this plus this is equal to f of 2k plus 4, and that shows that q of k plus 1 is true. So basically what we have done so far is, if pk and qk are true, it implies p of k plus 1 is true. And if p of k plus 1 and qk are true, it implies q of k plus 1 is true. So the spiral induction is complete. Using these two, we are proving the pk plus 1, and using pk plus 1 and qk, I can prove qk plus 1. So therefore, pn and qn are true for all n. So this is the method of spiral induction. We are able to show, using two propositions, we are able to prove the final conclusion. Both propositions are interrelated and they help us prove the other one. Okay. Let's look at the next one. This question can be done by double induction, but we'll use a different method. We'll use induction used twice rather than direct double induction. So we say let m on n be natural numbers. Prove for positive reals x1, x2, xn and y1, y2, yn if xi plus yi equal to 1 with I goes from 1 to n, then 1 minus x1, x2, xn power m plus 1 minus yi power m, y1 power m multiplied by 1 minus y2 power m, and so on till 1 minus yn power m is greater than equal to 1. So here there are two parameters, m and n. We have to first determine where we'll do the induction. Should we do the induction on n or should we do it on m? Here in this case, it is better to do the first induction on n, because it will be simpler to simplify when you are inducting on n, because the second term will just have an extra product. It will be more annoying to do it on m here. So you can try it yourself. You will realize that it is better to do induction on n. So if you do n is equal to 1, we have 1 minus x1 power m plus 1 minus y1 power m is greater than equal to 1. We have to show this. But 1 minus x1 power m is same as y1 power m plus 1 minus y1 power m, like this. And we are getting, this is going to be adding up to 1 is greater than equal to 1, which is true, right? Why did we do this? Because we know that x1 plus y1 is 1, right? So base case is easy to prove. So now we'll suppose that the proposition is true for n minus 1, where n is greater than equal to 2, right? We consider the n case of n. So in this case, we have this expression 1 minus x1, x2, xn power m plus 1 minus y1 power m, 1 minus y2 power m, and so on till 1 minus yn power m. Now we know that the proposition is true for n minus 1 terms, right? So we can write this as 1 minus x1, x2 till xn minus 1. And instead of xn, I can write 1 minus yn here. And whole power n plus, we can write this other terms as it is. So until 1 minus yn power n. Now, this will be greater than equal to, we can write it as 1 minus x1, x2, xn minus 1 plus x1, x2, xn minus 1 yn whole power m. I have just simplified this, plus here I am going to write this as 1 minus x1, x2, xn minus 1 whole power m multiplied by 1 minus yn power m. So what am I doing here? I am using the induction step for this n minus 1 term. Because it is true for n minus 1, what do I have? I have 1 minus x1, x2 till xn minus 1 whole power m plus 1 minus y1 power m so until 1 minus yn minus 1 power m is greater than equal to 1, right? So I can say that this part, which is what is present here, is greater than 1 minus this, right? Which is what I have written. And therefore the equality has changed to greater than equal to. I have not touched the first bracket at all. I have just simplified it. And I have used the inequality for n minus 1 in the second term, right? So now we'll say let A is equal to 1 minus x1, x2 till xn minus 1. And let B is equal to yn, right? This is just to simplify and make it look easier. So what is this expression? This expression is A plus 1 minus A into B whole power m plus this expression is B 1 minus B power m and this is 1 minus A power m. So we have plus 1 minus A power m and multiplied by 1 minus B power m, right? So we have our original expression is bigger than this, right? So what we have is the proposition for P of n is bigger than, we have A plus 1 minus A B whole power m plus 1 minus A power m, 1 minus B power m. And we need to show that this whole thing is greater than equal to 1. So it will be sufficient to show that this thing is greater than equal to 1, right? If we can prove this, we are already done, right? So now we will basically apply induction on this. A plus B minus AB whole power m plus 1 minus A power m, 1 minus B power m greater than equal to 1. We'll prove this by induction on m here in this state, right? So it is clearly valid for m is equal to 1. You can confirm that yourself. M is equal to 1, it will be valid. We'll assume that it is true. It is true for m minus 1. Assume its truth for m minus 1 and then try to simplify the mth case. So it is a plus b minus ab whole power m plus 1 minus a power m minus b power m plus a power m b power m minus 1. I have brought everything to this side. I want to show that this thing is greater than equal to 0. So I'm getting a plus b minus ab whole power m minus a power m minus b power m plus a power m b power m, right? Now we can say that this expression is greater than equal to uh, I can write it as a power m minus 1 plus b power m minus 1 minus a power m minus 1 b power m minus 1 multiplied by a plus b minus ab minus a power m minus b power m plus a power m b power m. What have I done here? I have split this into two parts. I have written it as a plus b minus ab power m minus 1 multiplied by a plus b minus ab. But I already know that this situation is true for m minus 1, right? So we know that a plus b minus ab power m minus 1 is greater than equal to this. So I have replaced it with that and I have written it like this, right? So we are getting a plus b minus ab whole power m minus am minus bm plus am bm is greater than equal to a power m minus 1 plus b power m minus 1 minus a power m minus 1 b power m minus 1 multiplied by a plus b minus ab minus a power m minus b power m plus a power m b power m. This is what I've done. I've used the induction statement for p of m minus 1 here, right? So if you simplify this RHS is equal to 2 a power m b power m plus a b m minus 1 plus b a m minus 1 minus a m b minus m minus 1 minus a m minus 1 b m minus a m b minus a b m. This is what the RHS is equal to right now. And we can factorize it like this. It is bm minus 1 minus bm, a minus am plus am minus 1 minus am and b minus b power m. Now we had chosen a and b in such a way that a was equal to 1 minus x1 x2 till xn minus 1 and b was equal to y of n and xi plus yi was equal to 1. So we know that xi and yi are less than 1 individually and a and b are also less than 1. Basically belong to 0 to 1, right? So that means that this term b power m minus 1 minus b power m is positive. This term is also positive. This term is positive and this term is also positive. So RHS is coming greater than equal to 0. So if RHS is greater than equal to 0, we know that this whole term is greater than equal to 0. And that is our induction step for P of M. P of M is true when we had assumed P of M minus 1, right? So our induction is basically complete on M. And once induction on M is complete, we have proved the original statement. We first did induction on N and then we did induction on M. This question can also be solved in a more concise way using double induction. So you should try that yourself. Look at the double induction method that I had explained before and apply it to this problem. It can be done using that. One last problem, which is a nice application of spiral induction again. We'll look at this one. Suppose there are 2n, where n is greater than 2 points in space in which any four of them are not in the same plane. Not in the same plane. Okay. If there are n square plus 1 line segments, n square plus 1 line segments connecting the points, prove that these line segments must constitute two triangles with a common side. So if there are 2n where n is greater than or equal to 2 points in space where any four of them are not in the same plane, and if there are n square plus 1 line segments connecting these points, we have to show that these line segments must have two triangles with a common side, right? So we denote the proposition that we have to prove P of n is P of n, where we say that there are 2n points with n square plus 1 line segments between them, such that any four of them are not in the same plane, and we have to show that these line segments make two triangles with a common side. That is my statement P of n. Okay. Now we will make a similar statement, but companion proposition Q of n. This Q of n proposition is this: let there be 2n plus 1 points in space. Same condition, no four are coplanar. No four of them are coplanar. If there are n square plus n plus 1 line segments connecting the points, connecting these points, we make the same claim. Then these line segments make two triangles with a common side. So I have constructed a similar proposition but slightly different. Now I have 2n plus 1 points, and I'm saying there are n square plus n plus 1 line segments connecting them. Earlier we had 2n points and n square plus 1 line segments where no four of them were coplanar. The final claim is the same. Line segments make two triangles with a common side, right? So let's think about how we'll go about doing this. The first step here is to show that P of 2 is true. This is the base case because n starts from 2, right? So think about it. P of 2 means there are 4 points which are non-coplanar, and there are n square plus 1 or 5 line segments. 5 line segments connecting them, right? So if there are 4 points in space and 5 line segments, then obviously the maximum number of line segments was 4C2 or 6, right? And then they would have made a tetrahedron. So if there are 4 points making a tetrahedron, you should have 6 edges. But this basically means that it is a tetrahedron with one edge deleted. Right? So if you draw the figure of a tetrahedron, you will realize that if you delete one edge, you still get two triangles with a common edge. For example, this triangle and this triangle. There is a common edge here, right? So anytime you have a tetrahedron with just one side deleted, that automatically means you can make two triangles with a common side there, right? So proposition is true for n is equal to 2, right? So we have proved the base case. Now what we will try to do is to show that suppose P of k is true, we want to show that Q of k is also true. Okay. So we are supposing that P of k is true, and we want to prove that Q of k is true. Actually, yeah. So let's consider for Q of k, we have to consider 2k plus 1 points. 2k plus 1 points in space that are connected by k square plus k plus 1 line segments. Right? No 4 of them are collinear. Now, we have this many points, these many line segments, no 4 of them are coplanar. Let A be a point here with the minimum least number of line segments, connected to it. So let's estimate the number of line segments that A must have. Number of line segments connected to A must be less than equal to K. Why? If A has K plus 1 line segments, then since A had the minimum number of line segments, all the other vertices also have K plus 1 line segments, right? At least K plus 1 or sometimes even more. So the total number of line segments will be 2K plus 1 vertices, each with K plus 1. And since we are doing a double counting of the line segments here, we'll divide by 2, right? So in this case, half of 2k plus 1 into k plus 1 is equal to k square plus k by 2 plus 1 by 2, right? Which is clearly greater than, this value is greater than k square plus k plus 1, right? Because k is greater than 2. We have already proved the base case of k is equal to 2. We are now doing k higher than 2, right? So this value is greater than k square plus k plus 1. So this is a contradiction. So A vertex cannot have k plus 1 line segments. The number of line segments connected to A is less than equal to k. That is true. We have proved it by contradiction by counting the total number of line segments possible. And in the hypothesis itself, we had this many total. We cannot exceed that, right? So now what we will do is we remove A point and all its line segments and all its lines. So now we'll be left with 2k points and k square plus 1 greater than equal to k square plus 1 lines, because A can have at most k. So when you remove at most k, you can have greater than equal to k square plus 1 lines joining them, right? Correct. So since we have assumed that P of k is true, P of k was what? If there are 2k points with k square plus 1 lines, then there is a triangle. There are two triangles with a common side there. Now we have satisfied the hypothesis for P of k, right? Because we have now 2k points and greater than k square plus 1 line. So there must be two triangles with a common side here, right? Two triangles with a common side must be present in this case. So basically what we have shown is that in this situation, when we took 2k plus 1 points and k square plus k plus 1 line segment, even there, when we removed A, we got the P of k thing, right? So Q of k is now coming out to be true, right? Q of k is true. Q of k was to prove that when we have this situation, we will have two triangles with a common side. We have just analyzed that situation, taken the point A with the least number of line segments connected to it, deleted it, and proved that the remaining figure still has two triangles with a common side. So obviously, if you don't delete it and keep the whole thing, that will also have two triangles with a common side, right? So Q of k is true. So far what we have achieved is we have proved P of 2 is true. And we have shown that if P of k is true, Q of k is true, right? Now, what we will assume is, suppose Q of k is true, we want to prove that P of k plus 1 is true, right? So for P of k plus 1's truth, we have to take 2k plus 2 points. And let's say there are k plus 1 whole square plus 1 lines, right? Again, we do the same method. A is the point with least line segments connected to it. How many should A have? So think about it. Number of line segments that A should have is less than equal to k plus 1. Why? Because if A had k plus 2, so we'll do k plus 2 into 2k plus 2 by half. That comes out to be k plus 1 whole square plus k plus 1. And that is greater than k plus 1 whole square plus 1. So if A had k plus 2 line segments connected to it, we are getting the total number of line segments of the whole figure will be bigger than what we have assumed, k plus 1 whole square plus 1. So the number of line segments for A must be less than equal to k plus 1. And now we'll do the same thing. We'll delete point A along with all the line segments. Along with all its line segments. So if you delete the point A and all its line segments, you'll end up with 2k plus 1 points. And how many line segments? You will have k plus 1 whole square plus 1 minus k minus 1, right? So this becomes equal to k square plus 2k minus k. So plus k plus 1. So you are ending up with 2k plus 1 points and k square plus 1, k plus 1 line segments. And we have already supposed that qk is true, right? Qk is true means 2k plus 1 points and this many line segments have two triangles with a common side, right? So since in this situation, we have deleted a point and gotten a situation where qk is true implies that there is two triangles with a common side. We know that here also there are two triangles with a common side. And therefore, we have established the truth of P of k plus 1. P of k plus 1 is now true, right? So now notice what has happened. We have basically said base case of P of 2. If you assume P of k, we have proved Q of k is true. And if you assume Q of k, P of k plus 1 is true. So we can keep doing it. We can keep doing going from 3 back to 2, and we can now prove that Q of k plus 1 is true, and so on. Therefore, we have basically finished our spiral induction. We have shown that P of n and Q of n are true for all n, right? So this is how you apply spiral induction. You have to think of that companion proposition. And here, notice we use the property of choosing a vertex with the least line segments connected to it, and then we deleted it to establish our proposition. So this is an interesting technique. You should go through the example again and try it yourself. And we'll continue in the next class with a new section. The new section will be complex numbers, and we'll look at complex number problems for Olympiads in the next week. Stay tuned for the next time.